Hello everyone, my name is Marko Šegon and I'm finishing the third year of my PhD study titled Composition of Cometary Dust from Fireball Observations under the supervision of Dr. Jiří Borovička. And last year I was talking about the transition from analog to digital meteor spectra. And since last year, I've been working on it together with my colleague Vlastimil Vojacek, and we have come to understand a few more things. And today's talk will be a follow-up to last year's. Starting with a brief overview of the equipment we are using and our previous work, and then mostly discussing the newly developed flat field and some spectral sensitivity remarks. So first of all, we are acquiring our data from 11 stations of the European Fireball network, scattered across Czech Republic, Slovakia, and Germany. And each of these stations is comprised of the SDAFO and DAFO systems. You've heard already something about them. So SDAFO stands for Spectral Digital Autonomous Fireball Observatory. And each of those systems is equipped with 2 digital Canon EOS 6D cameras with 1000 groove per millimeter plastic holographic gratings. And they have their infrared cut filter removed, extending the spectral range to about 3,800 to 9,000 angstroms. You can find all of this data and much more in the paper published in the proceedings of the IMC 2018, so I will not discuss more about it. Basically, last year, I gave you a full rundown of the analysis process that we are using to both acquire and analyze our spectra. So the first part, including photometry, astrometry, and spectrum acquisition from the image, is done in the FishScan software developed by Dr. Borovička, while the subsequent steps of the analysis are done in the Python codes which I've developed over the past few years. Unfortunately, both of those software aren't commercially available yet. My Python codes might become open source by the end of my study when I test it out thoroughly, so that's maybe something to look forward to. Basically, the most important parts of last year's talk was this plot, comparing spectra of the same meteor captured by both analog and digital stations. So the analog camera was plotted in black here, and right away you can tell that it's behaving completely differently than the digital spectrum. And we have attributed these differences to poorly determined spectral sensitivity. And haven't really touched much on it since last year. We focused more on the digital spectra and the differences between the digital spectra, especially in this part of the region. The rest seems quite consistent. However, we've attributed last year these errors to measurement errors, measurement uncertainties, and a lower spectral sensitivity in that part of the spectrum. However, since last year, we've come to understand that there's more going on. And one of the key aspects, and basically the main part of the talk, will be regarding the flat field we were using and we should have used. So in slitless spectroscopy, actually the flat field is both position and wavelength dependent. And this is something that, at least to our knowledge, nobody's really accounting for. And this wavelength dependency is not covered by the spectral sensitivity. It's a completely different aspect of it. And these position and wavelength dependencies are really intertwined in some way. So there is no easy way of distinguishing between them and correcting them one by one. What really should be done is sort of creating a different flat field at each wavelength and creating sort of a cube of points. This is a very complex matter and something that is done, for example, on the Hubble Space Telescope and such projects. And it would require, in principle, some sophisticated equipment. But of course, given our budgets, we can't really go to such extents. But what we really can do is we can create some DIY laboratory setup to help us characterize this, at least to some extent. So first of all, what we really need is a light source. Unfortunately, Rudolf here won't do us much good. We require a linear spectrum with well-resolved profiles, preferably spread out across a wide spectral range. And in fact, we've settled down on using a fluorescent light source, a lamp, basically, with a spectrum such as this one. And while it doesn't cover the full extent of our wavelength range, not one source capable of doing that was available to us. So we focused on this one because it covers the most important area to us, which is from about 4,000 to 600, 500 angstroms. It actually stretches out another 1,000 angstrom, but the lines there are of very low signal to noise ratio, so they aren't to be taken very reliably. In any case, once you have no light source, you require a dark room, as seen on the image. And most importantly, you really require a colleague with nerves of steel, such as Vlastimil, who is willing to repeatedly take images across of the light source in different positions in the field of view and do it for several different gratings to make sure everything is consistent, and as many times as needed until we get the setup actually right. And this is what the setup looks like, as DIY as it gets, basically, but I will not go into the details because I don't have the time, but you have these cameras and gratings, which are the exact same ones as used on the stations, and you have a light source separated from about 4 and 5 meters from the camera, and you're taking images of the spectrum in different parts of the field of view. Now, once you've taken all the images, this is what it looks like, just a composite image of all of them plotted on one image. And once you analyze this and plot the positions, this is basically just to check that we're determining the positions of the spectra correctly, because we will need. So now we've finally come to the point where we can actually say something about the correction itself, how to apply it. And first of all, I would like to distinguish between the wavelength independent and wavelength dependent parts. Both of these are position dependent as well, but it's quite easier to approach it in this sort of way. So first of all, what you need to do is you need to integrate the total intensity of the light source, or the zero order, on the image and plot it versus the position in the field of view. And once you do that, you get something like this. First of all, we used to do this type of correction before as well, but we're using a radial polynomial function. But we've come to realize that while this is symmetrical in the x-axis, it's not symmetrical in the y-axis. Actually, the top part of the image is brighter in all of the cases than the bottom part of the image. And this is something that has purely to do with the internal structure of the camera, and not something that we can fix by changing something in the camera, but simply by applying a different kind of function, second-degree polynomial function in both x and y, as you can see below the image. Okay, that sort of covers the wavelength independent parts. Now let's talk about the wavelength dependent parts of the flat field. So first of all, we need to correct all the spectra for wavelengths. So this is actually all of the spectra plotted at the same time. And once we have wavelength calibrated, we can divide them into different wavelength segments. And to each wavelength segment, we can attribute its total intensity, its average wavelength, and the position of the spectral line in the field of view. And if we plot for just one of these segments, the total intensity versus the position of the line in the field of view, we get something like this. So this is prior to applying the previously determined wavelength independent part of the flat field. So we have something like this, and if we plot it for all the different wavelength segments and color them accordingly, we get something like this. And this is, again, symmetrical with respect to the x-axis, so we can mirror the data, and we're left with something like this. Now, finally, we can apply that flat field correction, which we've determined before. And in the cases where this would be a slit spectroscopy experiment, we would expect, after applying that part of the correction, to have a flat surface at about 1.0 with some deviations. And what we're actually getting is something like this. Mind you, these are absolute intensities. In terms of relative intensities, once the spectra are scaled, it's nothing, it's a lot smaller difference than here. However, we still need to address things. So this is just to show it from different perspectives. And this is by any means not something which is 1.0. So isolating only one of these wavelength segments now and applying a polynomial function of a high degree, which is purely meant to mathematically describe this. There is no physics involved in the function. We can describe this behavior for different wavelengths and get these surfaces for each of the wavelengths. Thank you. Basically, once you apply the correction obtained this way to the laboratory spectra back, I will not go into the details how it's done because it is quite complicated, but you can contact me about it and a paper will be published with step-by-step instructions. Once you apply it back to the original laboratory spectra used to create the fit, these are the leftover maximal deviations, and the standard deviation is about 5% or less in the main parts that we are interested in. As expected, it's worse around the edges of the field of view and for lines with a low signal-to-noise ratio. However, this really doesn't tell you much. Let's take a look at what the spectra looked like before the correction was applied. So this is all the laboratory spectra plotted before. This is after the correction and after taking out some outliers at the very edges of the field of view, we get something like this. So this is a very significant improvement, obviously. But how does it fare when we try it out on real meteor spectra? So this is a composite image of the same meteor captured from 7 different stations and in different parts of the field of view. And this is what the uncorrected spectra look like. And right away, it's quite consistent already, aside from perhaps some stations in the sodium line. This won't get fixed by this correction in particular, but we're looking into that as well. However, I would like to point your attention towards this part, which now, after applying the correction, looks quite better. The rest of the range, in terms of comparison, there's not much difference. But what you really have to keep in mind is that these lines haven't changed much relative to each other. These have relative intensities of lines in this part, and this part will change, and you need to take it into account. Otherwise, you're not going to get reliable line ratios and abundances which are computed from it. So just a very quick note on spectral sensitivity. We've coupled it basically with computing the atmospheric extinction as well, and did the correction by determining the spectral sensitivity factors for different wavelength parts using a spectra of Venus on a clear night. However, these spectra were not accounted for the new flat field previously, and now we've recomputed it so that is taken into account, and we're getting a more reliable curve. And basically, I will finish with this. This is the last slide, just the status of the work. And the orange marks basically mean that it's in the implementation phases, but it still hasn't been implemented in the code, but we know how to do it. So I thank you for your attention, and I'm open to all questions, remarks, and that's it.